So when we finished class last week, we discussed what amphoterism means and how we can look at amphoterism in terms of a complex ion formation that can potentially form. So the example problem that we kind of addressed and talked through conceptually was, what is the molar solubility of aluminum hydroxide, which is AlOH3, in 15 molar ammonia? So this is the ultimate question that we're going to try to answer here. Basically what happens is when you put aluminum hydroxide in aqueous solution, so we have AlOH3 as a solid in equilibrium with aluminum 3 plus in aqueous solution plus 3 OH minus ions in aqueous solution. Our KSP for this is equal to 4.6 times 10 to the minus 33. So this is telling us that aluminum hydroxide is not going to readily dissolve in aqueous solution. But what happens is, when we take that aluminum 3 plus and we add 4 equivalents of OH minus ion in solution, we have an equilibrium expression that forms a complex ion, which is AlOH4 minus. The Kf, or the formation constant of this complex ion, is 7.7 times 10 to the 33rd power. So this is going to give us an overall expression of, we notice that aluminum 3 plus is both a reactant and a product in this overall equilibrium expression. So we have AlOH3 as a solid, plus we have 3 hydroxides as a product and 4 as a reactant. So it's going to be plus 1 OH minus ion in solution. That's going to be in equilibrium with AlOH4 minus. The K for this expression is going to be the KSP times the Kf, which when these are multiplied together, we get 35. A value of 35 is going to tell us that this equilibrium is going to lie to the right, or it's going to lie on the side of the complex ion formation. So now what we're set to do is take this overall expression that's happening in solution, we can set up an ice table, and we can go on our merry little way to solve this problem. The solid concentration does not change throughout the equilibrium, so we can ignore that. And we're asked for this molar solubility in 15 molar ammonia, which we need to know the initial concentration of the hydroxide ion and the complex ion in order to perform this calculation. The thing that's unfortunate is that we're not given a hydroxide ion concentration. So the question is, what's the initial concentration of this hydroxide ion? We have 15 molar ammonia. Remember, and I kind of alluded to this last week, that if we have ammonia in aqueous solution, anytime that's added to water, an equilibrium is set up between NH4 plus ions in solution plus OH minus ions in solution. And the Kb for this particular expression is 1.8 times 10 to the minus 5. And that can be looked up in a Kb table. So in order to figure out what the initial concentration of the hydroxide ions we have to set up an ice table and perform an extra step for this particular reaction. Our initial concentration of ammonia is going to be 15. The water, since it's a pure liquid, the concentration is going to remain constant, and we can ignore that. And we have 0 NH4 plus and 0 OH minus to begin. The change in concentration is going to be minus X for the ammonia, plus X for the NH4 plus, and plus X for the OH minus. So our equilibrium concentrations are going to be 15 minus x, x, and x. Our Kb expression is going to be equal to the concentration of x times the concentration of x divided by 15 minus x, and that's going to equal 1.8 times 10 to the minus 5. If we go through and we do the algebra, x is going to equal, if you notice from our ice table, x is really what we want, which is the hydroxide ion concentration at equilibrium. So x equals our OH minus concentration, which is going to equal 1.6 times 10 to the minus 2. This concentration right here is our initial OH minus concentration for the equilibrium that we established in the previous step here. So now we know the OH minus concentration that we can plug into the top ice table, which is going to be 1.6 times 10 to the minus 2. And in this particular equilibrium, initially we don't have any concentration of our complex ion, but when we allow this to reach equilibrium, we're going to have minus x for the concentration of the hydroxide ion and plus x for the concentration of our complex ion. So at equilibrium, our OH minus concentration is going to be 1.6 times 10 to the minus 2 minus x, and our complex ion concentration is going to be x. We said that our equilibrium constant is going to be the KSP times the KF, which equals 35. So we can set up a K expression that in this case, it's going to be products over reactants. So it's going to be the concentration of our Al OH4 minus divided by the OH minus concentration. So this is going to be x divided by 1.6 times 10 to the minus 2 minus x. And that is equal to 35. If we go through and we solve for this, x is going to be equal to 0.016 molar. So again, I always emphasize that we just solve for x. So what exactly is that x? Anytime we write an ice table up here, we can assume that if x moles of aluminum hydroxide dissolves, we can use those variables throughout here. So our x is going to be related back to the moles of aluminum hydroxide solid that dissolve. Okay, so x in this case is going to be the molar solubility. So to kind of jump back and recap what we've kind of just done here and reflect on what's going on, you have a particular solid. Okay, it's aluminum hydroxide. We place that in solution. When we place that in solution, think about the equilibrium expression that's being established. So in our particular beaker, we're going to have a lot of solid aluminum hydroxide. We're going to have a small amount of aluminum ions in solution and a small amount of hydroxide ions in solution. Then you add another reagent to this beaker. That reagent is ammonia. If you look at the complex ion table, aluminum and ammonia do not form complex ions in solution. But aluminum and the hydroxide ion do form complex ions in solution. Ammonia is a base. We have concentrated ammonia. It's going to add a decent amount of hydroxide ions to that particular solution. In doing so, we're going to facilitate this complex ion formation, which introduces another equilibria that is happening simultaneously to the first one with the aluminum. When you have two simultaneous equilibria that are happening, you need to add those together to get one large equilibrium expression. Then you need to use the initial concentrations from the reagents given. In this case, we have ammonia, right? We know that ammonia is a base, so it's going to produce hydroxide ions. Just how many hydroxide ions are produced is going to be dictated by the concentration of the ammonia. we're dealing with a very highly concentrated ammonia solution right here. Okay? So you then set up the ice table after determining your concentration of hydroxide from the bottom ice table down here. You can set everything up and you can solve for, in this case, X, which is the molar solubility of aluminum hydroxide in a concentrated solution of ammonia. Okay?